Hello, so I'm Jennifer Hassler. I'm professor at Georgia Institute of Technology, and I want to talk about cryogenic AI for quantum systems. Now, this makes for a very interesting discussion because you may or may not think about AI, quantum, and cryogenic all in the same discussion, but I want to kind of introduce an idea where we might imagine these being all together. Now, when I talk about AI, I want to talk about this in a broad definition. Having looked at this field for a long time, there are different times when AI means different things. So this will definitely include all of your neural networks, your deep neural networks, your classifiers, your machine learning, and what is classically AI, as well as neuromorphic and physical computing. And I'll often lump a lot of this into physical computing kinds of approaches. So the big question is, well, why would I want to consider any of the kind of physical techniques to do this? Well, imagine I have an interesting problem where I have a whole range of qubits. And I can imagine having a whole bunch of them here, and then I maybe have some LNA, which might also have some mixtures to them, and then I still need to read out that resulting signal and find a reasonable structure to it. Now, a lot of other classical problems may have a similar situation. I might be in a situation where I need to deal with some sort of sensing problem to make this work. Well, if I'm in this situation, what I'm going to see is typically I'll have signals 25 to say 200 megahertz, are rough kind of numbers. These are continuous time signals, and that typically I need to be able to then sample these, but there's only a small fraction of this that I'm really eventually trying to get, and I want to be able to look at this and classify and build this, because eventually I'm going to have very, very low frequency kinds of events and processing and things that I need to do that. In fact, a lot of the results are often digital. If it's quantum computing, often the results are a particular digital state that I want to use, or a low resolution kind of output is what I'm looking at. Similar sort of thing would be true in a sensing space. So you might just say, well, fine, just put a bunch of analog to digital converters. I'm sure those are near free. Well, may or may not be, depending on how you look at the world, but you can often do a lot of them. And say you put like 100 megahertz ones and run them at 10 bits. Well, what you end up finding is that, if I had 100 qubits, the amount of data that needs to get transmitted is probably around the range of about 250 gigabits per second. That's quite a bit of data for what is a relatively small problem. If you start to scale this up to interesting size nodes, up to just even a million qubits, you start to talk about petabits of data that you have to get across there. So this is an incredible amount of complexity. There's a huge amount of energy to transfer all of this bits. And you're really trying to deal with a continuous process that eventually you're recovering later. There's really quite a lot of complexity to this entire structure. So you look at this and you think, I've got a really interesting problem, and you might say, well, is there any alternatives to trying to solve this particular problem? Well, imagine I could build some sort of an initial classifier network in this. And again, if it's purely digital, it may or may not seem like I'm getting a huge advantage by grouping all these LNAs locally and making this work. But imagine it's done in a physical computing structure where I get some initial classification and compression and sort of refinement of the data right at the sensor that has a chance of actually improving the overall SNR of the refined data. It has an ability to actually do some of the processing really locally, but there's some other bigger pieces to it, which often are in terms of advantages of having basically low area computation, nearly very low energy or power. Small area means I can put them right with the sensors, almost no latency, so I don't really have to worry about that overhead. And this is what we typically would talk about in terms of physical computing. And when I mean physical computing, it is at one level computing over real values. And we can kind of talk about different examples of it. Analog would be in that place. People talk about neuromorphic, which is kind of, one of the classes of AI. We could go back and forth and talk about optical systems, which you sometimes use in neuromorphic or use in other kinds of, and use in some of these classifier structures or AI techniques. But also quantum would also fit in that same space. And so this turns out to be an interesting way to kind of have a physical system, real value computing, connect to another real value computing. And we may kind of return back to that in a little bit. And so you go, well, what happens when I do this? Well, if I then take this structure, have a bunch of ADCs locally, the ADCs can be significantly lower in terms of the bit rate. I can really, I can get a lower sort of complexity there and so forth. And what you might imagine is, say the average bit rate goes down by 5x, the sampling events, I don't need to worry about the Nyquist part of it, so that changes it. Number of IOs, just say, decreases by 10x, which is a fairly conservative number, and you get a 100x decrease. And you might say, well, okay, that's really cool. What is that difference? Well, that goes from, for 1,000 qubits going from 2.5 terabits to just 25 gigabits per second. This is a huge improvement from a complexity standpoint if you're the one having to build the system. So these turn out to be really, really big deals. And then after that, you can have an additional classifier networks that are done, say purely digitally, purely in another sort of structure, but even that load gets reduced in the end. And so I think there's some really interesting opportunities here, and you think, okay, this is great. So you say, okay, this might be a good idea, so what's possible? And what's possible in these ideas going from sensors to some form of classification, maybe all the way through, maybe in some case partial, but you always are really looking at questions from sensors all the way to the end. And so what we're going to talk about here is, what could you imagine doing from an analog computing perspective, or again, related classifiers and related techniques, and what's possible in this space. So let us continue with this presentation. So one of the discussions here is going to be talking about field programmable analog arrays. These are basically very similar to FPGAs. In fact, FPGAs are used in the back-end processing for a lot of these systems, but is in an analog and mixed signal structure. And the biggest difference with it is I basically have analog elements along with the logic and routing. And this can be used obviously for sensor interfaces, but could also be used for the whole range of networks and neural network structures. For example, you could imagine an acoustic classification starting off with a microphone, going all the way to command word recognition, say looking for a word like the word dark in a typical timid database, and all of a sudden you realize, oh yeah, I can actually pick off this one word in something that's like 23 microwatts of power, almost zero latency out of the structure. Basically microseconds of latency out of the structure, and with very, very high, very, very robust. And you can look at this for a whole range of problems. You can do learning, classification, all of these things. These kinds of structures are often done in fairly inexpensive processes at first because of the cost, but there's also good work in showing that this can be done all the way into 40, 45 nanometer with development actually in 14 nanometer discussions. And so this has been an area with a lot of possibilities. The key thing in these structures is the programmability, and you often talk about having these floating gate elements, which are all done in standard CMOS. So we're not adding anything to the process just to be, and then being able to give us programmability. So on a typical chip, like let's say this particular device, particular FPAA device that was developed at Georgia Tech about 6 years ago, what we find is that we have somewhere in the range of about 1 million analog programmable floating gate elements in the structure. And we say analog programmable is to like 14 bits of precision, and that can be used in all sorts of different types of analog aspects. And it also turns out that some of this can actually be looked at in a cryo space, and I'll talk a little bit about this towards the end. But the fact that there are discussions of this is data showing some initial characterization that we did with floating gates, and also did some FPAA structures in collaboration with David Riley's group at University of Sydney. And so you can actually talk about classification, and this is a little more in-depth on what one of them would look like. This was an acoustic classifier problem where it was designed to really be fairly low power in the microvolt microwatt kind of ranges. And what you end up finding is you can actually do a full classification from one end to the other. We actually took a data set that was developed by DARPA, made it about 10 times harder, and actually ended up getting basically perfect classification out of this, and actually was able to do all the training and learning on the chip, which is actually very relevant to be able to say I can do in-field training, changing, programming, or just program it in a particular way. But I think for some of these techniques, we're going to find that the online training will be very valuable. So you could imagine that taking this structure that exists, and then if I needed to put this into a cryo kind of space, these are things that are certainly possible. One might also wonder if there's tools for this, and there is a whole tool infrastructure, whole open source tools that are done in Scilab, which is basically Scilab and XCOS, which is basically an open source version, open source clone of MATLAB and Simulink. There's a whole tool infrastructure. One could get into this. It gets quite extensive, but we developed all of this around also doing the chips, and this has been a huge deal. The interesting thing of developing the tool infrastructures is it also gives us a possibility of talking about building, taking the results at some point at this stage, and actually with, say a standard cell library could actually start targeting this. And this is actually a discussion that is at ISCIS in 2020, sort of talking about the initial possibilities. So you could imagine doing things with FPAs, you could imagine doing custom design, you could imagine a whole mixture of things depending on the conversation and the application you're looking for. And in some sense, this makes a lot of sense to be able to be using a physical computing medium to interface to, say, something that's quantum, or even some physics experiments, which are also real valued structures, because not only are there good conversations of how to talk about high-level abstraction and how to build this up, whether that be the numerical analysis side of it, the abstracting and building abstraction blocks, and as well as getting good architectural conversations, what you find is that almost everything in the physical space, there is some sort of connection and relation to all of them that definitely can be talked about in a sort of unified computing model that gives you something that looks a little different from what you'd have in the digital space. And this is sort of very early work that's kind of showing that there's not only a unification of these ideas, but it potentially has the opportunity to be much more sophisticated than what we would have seen, than what we'd see with sort of digital Turing machines. Now, I'm sure there's some people thinking, wait, you're just floating gate devices and various types of memory in this, so what are we going to do with radiation, right? Because that's really the elephant in the room. And the comment is, well, we're not ignoring that, and we definitely get that. And we also understand that we need to kind of work through that question to some extent and try to get a solution there. And we know that the radiation effects are important in certain cases and not others, particularly if you go into cryo areas of space and certain instrumentation for certain experimental measurements, it becomes very important. And to be fair, this is still somewhat of an open question, particularly when you start talking about these analog computing devices. Now, at a very simple level, radiation gives you carrier generation that tends to give you charge in an insulator, and that can either cause traps to occur in the insulator, or you can get charge stuck into a floating gate. And so thinking about that's important, but it's also, as we understand with some of the other floating gate aspects in terms of retention and so forth, is probably a little more complex depending on how you use it. And there seems like there's some interesting questions to still be asked of how do you actually utilize some of the same circuit techniques in this space, because there may be some good robustness and possible opportunities there. Certainly you have the opportunity of having sort of close differential floating gate elements because you have multiple devices affected in scaled down structures, while at the same time the common mode tells you what your radiation levels are, and so you can kind of use that to kind of help do some correction. In fact, you can take that extent and actually extend it out further and to look at normalized sort of vector metrics and see what you get in those spaces. And then on top of that, what you can also talk about is get a whole range of just reprogrammability in system in terms of various measures you get around that. There's been a huge amount of work looked at in terms of built-in self-test techniques in this, and this would be something we would utilize and utilize probably pretty frequently in the operation of a structure to go, okay, how close or how far away have things drifted or moved away? And so I think there's sort of an open question of how much and what does that mean for what application. But sort of summarizing things out, what you end up finding is that I think for the physical AI, for cryo or quantum, there's a huge opportunity for the sort of physical AI broadly defined to reduce the area energy complexity and really open up some new opportunities there. I think what you find is that it's really natural for one physical platform to interface to another physical platform. What you also can see is that you get a significant number of sort of room temperature physical AI demonstrations, and I think what these things should translate into a cryospace with some really sort of minor sort of changes in circuitry and approaches, although there's still a huge amount to understand on the cryo IC design. I think that's a huge opportunity there, as well as sort of what happens with floating gate circuits and systems, as well as any other memory technology you would use, and you would need a memory technology to do this, to sort of handle, in sort of higher radiation environments where that becomes an issue. But the fortunate thing is a lot of things can be looked at in terms of the cryospace, and there's a translation to it. Fortunately, transistors have very similar band structures, whether they be at 300K, 77K, or even as you get down to 4K, it's very still similar enough. Obviously, some issues of subthreshold not being, all that large, being pretty small, and things are going to be above threshold. But I think there's a huge opportunity, and it's really clear that the threshold mismatch elimination is essential, the programmability is essential. So I think there's a huge opportunity there, and I look forward to kind of seeing what potentially could happen going forward.